Cool. So our session should now be recording. There we go. So in this morning's lesson, just briefly, what I want to talk about are these ideas about reflections around an axis. So what we've looked at since really we started talking about, since really we're starting to talk about linear expressions, quadratic expressions, cubic/polynomials, and moving through, one of the key focuses that we've had has been sketching all our different functions and seeing how our functions behave on a number plane when we change values. What makes any function we graph move left or right? What makes it move up and down? What changes its scale? What makes it larger? When I say larger, moves the arms away from the y-axis. What brings its arms back into an x-axis? Tightens up or stretches out. We've been looking at those kind of features and being able to identify that. And I think one of the main idea behind all of that was exactly like that last question that I answered there with Joe with question 3. It's that ability to sketch something, to be able to see a function, be able to generate a quick sketch of that function to help you problem solve. We all know that a picture tells 1,000 words. So if you can quickly sketch a function to describe some of its key features, it gives you kind of an idea, kind of a head start on where you might be able to take a direction when we ask you to answer a specific question with it. One of the last things moving forward with polynomials and again hyperbolas and other different functions is we've got this, we're able to reflect stuff around an axis with a very quite simple change in the notation of our function. So before we get into that, I just want to start off with the function x squared minus 2x. Can you quickly start typing in and describing some of the key features of that? The first thing I want you to start off with, is it a polynomial? If it's a polynomial, what degree is it? And lead from there. Cool. Come at me with your answers. Yes, it is a polynomial. It's a polynomial of degree 2. What does that tell us? Yeah, it's a parabola. It's a quadratic, which equals a parabola graph. What else do we know about this particular parabola? Yeah, it's positive. Its leading term is positive. So if it's positive, what does that mean in terms of our if it's positive, what does that mean in terms of its arms? Both arms are up, that's right. So we're having both arms up, going up. Cool. Because it's a parabola, what are some of the other key features that we know about parabolas? Yeah, it's symmetrical. So because it's symmetrical, it must have an axis of symmetry. Sorry, Rhea, that the internet's playing up. I think mine's doing a bit as well. Josh, I can't do John Travolta because it's not an odd power, it's an even power because it's degree 2. John Travolta only comes out with odd powers, mate. Apologies. Axis of symmetry. What is its axis of symmetry? Actually, David, no, this one's not 0, 0. Remember the axis of symmetry, it's there in the quadratic formula. It's yes, apology, pronounce name. Yeah, it's minus b over 2a. So minus b over 2a is our axis of symmetry, which in this equation is going to be minus of minus 2 all over 2 lots of 1, which, funny enough, becomes 1. So our axis of symmetry is 1. If our axis of symmetry is 1, what else do we know about it? Do we have a y-intercept? Yeah, it's y-intercept 0. Cool. We know it's 0 because if we go back up to the original function, we have no random constant plus c shoved at the end of it. So our y-intercept 0. If it's y-intercept 0, what are our x-intercepts? And what methods would we use to find our x-intercepts with this graph? Yeah, we'd factorize. Cool. If we could factorize, not much, Rhea. We're still talking about key features of this polynomial. We could factorize. What could be another method that we could use to find the x-intercepts of an equation? I agree, factorizing is the best method here, but what's another method, another tool we have up our sleeve? Yes, the quadratic formula. Definitely we could use, yeah, Josh, we could graph it, but that means we'd have to create a table of values to plot it to graph it really accurately to find our x-intercepts. The two ways I would suggest would be factorize and then quadratic formula. But this one's going to factorize to x outside of x minus 2. That's what we factorize. So if we've just factorized it to x outside of x minus 2, what are our x-intercepts going to be? 0 and 2. Beautiful. So through all that, we've kind of got a really good mental image about what this parabola is going to look like. I'll just change colors, and down the bottom right here. Oh, actually, there's one thing we're missing. Does anyone know what is one thing that we haven't described yet so far? Yeah, the vertex, the location of the vertex. I know the vertex is happening at x equals 1. The vertex lies on that vertical line x equals 1. Yes, spot on. And when we put 1 in there, 1 squared, oh, Dave, just double check our maths. 1 squared minus 2 is -1, isn't it? So we have a vertex is at 1 and -1. Cool. So what we know is we can draw a parabola that kind of looks like that. We know both arms are up. I know that one, what do we say, is 2. Well, that was dodgy. That we know is 0, and its vertex is going to be 1, -1. And that's roughly what that's going to look. Is everyone happy with that? See how identifying all our key features kind of made it really easy to sketch a parabola straight away. And what we just did there, we do for any polynomial. No, we don't have to worry about polynomial long division. That's only if you're an extension student. For us, polynomials, it's just we'll give you polynomials in factored form to sketch. We can ask you to add and subtract polynomials, but that's kind of where it stops for us. And when I say add and subtract polynomials, that's where you have your composite function. You get function of x plus the function of g of x, add them together. So that makes life a little bit easy for us in this course. Cool. So going through that, we've identified the key features. We've got a good mental image about what this parabola looks like. Can I get you to spend 2 minutes quickly completing that table of values for me for this function? Some of those we already know answers for argument's sake. When x equals 0, we know that y equals 0. When then at x equals 2, we know that y equaled 0 because they're our x-intercepts. At 1, we know we had -1. Cool. All right. When we chuck 3 squared in there, x equals 4. Yeah, x equals 4 is 8. If x equals 4 is 8, what about x equals 3? Yeah, thanks, Ruben. We've got 3, we have 3, and we have 8. And again, we can see again, there's that symmetrical nature of a parabola. And all I have hidden down here is my favorite graphing software, Desmos, with all those points placed on there. And if I just zoom out a little bit, kind of matches our sketch pretty well that we came up with. Everyone comfortable with that? Cool. All right. Now, we're going to do the exact same table of values again, but this time we're going to tweak it slightly. I want to do that table of values but we're going to focus on negative f of x. And sorry, I've got a bit of a typo here. That's not actually y in there. That should actually be f of x. Does everyone agree with that? That my bottom row shouldn't be y. It should be f of x, because I've described my graph in negative f of x. Cool. But here, if we have a look at this, let's take a closer look at, I said, let's describe it for negative f of x. So really, when I've got this negative at the front of f of x, if we go back to that previous table of values that we've done, 8, 3, 0, minus 1, 0, 3, 8, they're all the values for f of x. This table, I want negative f of x. So all we really need to do is get our values for f of x and multiply them by negative 1. Does that make sense to everyone? Yep. So I'll just zoom out again. Our first value there for negative 2 was 8. So 8 multiplied by negative 1 just becomes negative 8. And 3 multiplied by negative 1 becomes negative 3. Well, 0, that's easy. 0, 0. Minus 1 becomes 1. We have 0, minus 3, and negative 8. Can someone describe what they think's just happened here? Yeah, it's gone upside down. It's now concave down. Great language. Upside down, concave down, flipped. What I'm going to do here, inverted. I'm going to stop showing my iPad for a moment. I am going to come back to that, but I want to flick back over here. And I want to go to Desmos. And in Desmos here, I'm just going to type the function of x was equal to x squared minus 2x. Everyone's comfortable. That was our original function. Now, Desmos, again, every math teacher's favorite tool. Not every math teacher. Some teachers prefer GeoGebra. I like Desmos. Desmos lets me do this pretty cool, sneaky thing where I can type in negative f of x, and can you all see it's now graphed the graph of negative f of x. What Desmos has done is gone, oh, look, you had your function of x as being x squared minus 2x, but then you've told me to graph negative f of x, so I'm just going to get this, and like you all described, turned it upside down, flipped it around. I'll come back here, I'll minimize that one there. Can anyone else, it's very good computer system program. Can anyone else, we've had some really good words there. Does everyone agree what we've just done here is we've reflected our y values over an x-axis? Can everyone see that? That when our parabola was up, all those y values were reflected around an x-axis. So if I just flick you back to my iPad right now, find where I put my pen, and go back here, when we put a negative sign at the front of our f of x, what we are doing is we are reflecting all our y coordinates over the x-axis to become negative coordinates. So zooming in, here you can see the black line, which was our original graph of the function of x was x squared minus 2x. And all those red points that I've got there, you can see that this point here has been reflected to there. This point reflected to there, reflected. Notice anything that's on our x-axis didn't move. Because it was neither above nor below. It was on the x-axis. Our x-axis becomes then our axis of symmetry, and we flip everything around the x-axis. So these went down here, and that went down there. Is everyone comfortable with that? Yeah, cool. So what we have, whenever we see, if I say, here's some function, so let's go down here, and I give you h of x cubed. Now we have our odd power. And then I ask you to graph negative h of x. Yes, it is a Travolta curve. When I ask you to graph negative h of x here, and I'll do that in a second, what I'm asking you to do is, can you reflect that graph over our x-axis? Is that all right? Beautiful. All right, so what we're going to do quickly in the next few minutes is do exactly what we did with the previous function with this function, go through those points. I'll let you type the Desmos and get it to reflect for you and match up. So h of x, its key features. It's a polynomial of degree 3, which is a, oh, that was dodgy, cubic curve. Cool. Tell me something else about it. If it's degree 3, what about its the leading term? What's the leading term? Leading term is positive 1. Yep. Because it's positive, it's our Travolta style. It starts down left and ends up right. What else do we know about it? What about x-intercepts, y-intercepts? Yeah, they're both 0. What else is something important about a cubic? What's another feature of a cubic that I said we're going to discuss later down the track? Yeah, it's got a wiggle. The wiggle. What's the technical name for the wiggle? And please don't tell me red, yellow, blue, and purple. Yeah, the point of inflection. So if we were to graph this quickly, a quick sketch of it, we're going to have come up, it's going to wiggle through the origin and keep on its path. And yeah, our point of inflection in this case is the origin. And remember, thinking about our spoons, the point of inflection is just a change in concavity. And again, that's U12 concept. We'll come back down to that one later. Moving on, remember these notes are going to be up on Canvas. What are my values here when I throw these ones in? And again, same typo as earlier. That should be h of x. Minus 8, yeah, negative 8, negative 1, 0, 1, 8. And that is just going to give us our cubic curve, which is what we talked about. And we can see at 0, it's concave down and then concave up through our wiggle. Moving on, let's repeat that with negative h of x. What's negative h of x going to give us? It's just going to change all the signs, isn't it? Everyone agree? The signs, yeah, our signs are going to change. We've got 8, 1, 0, minus 1, minus 8. So if you were to go through on Desmos, and let's do that just quickly, because we love using Desmos. Let's turn these guys off. And let's go h of x is equal to x to the power of 3. And we know we can do negative h of x. And that purple is just our reflection. which is an interesting reflection as well. Can anyone tell me what's interesting about that reflection as well? No, Alex, it's not two parabolas. It's just the green is one cube, the purple's the other cube. A cubic doesn't have an axis of symmetry, but it looks like it's also being reflected around the y-axis. What we've actually done by putting negative h of x in, we have changed the values of our y-coordinates. But what do we know about the graph of h cubed, x cubed in itself? I'm just going to bring to my iPad again. It appeared to reflect around the y-axis. Now, that's what it appeared to do. It didn't. It actually, oh, hello, around the x-axis. Now, the reason it appeared to reflect h of x, it is an odd function. And because it is an odd function, it appeared as if it reflected around the y-axis. But what we actually did, and you can see down here, is this point got moved to down here. This point gets moved to here. That point gets shifted there. That point gets shifted there. And what we have, whoops, let's undo that. Well, that's a pretty dodgy wiggle. We get that, which appears though as though it reflected around the y-axis, but what we actually did is we reflected around the x-axis. It's the reason that it looks like we just did that one as well, is that it is an odd function. Everyone okay with that? Everyone understands what I mean by an odd function as well? Everyone remembers odd and even functions? Yeah, cool. Does anyone have any questions on anything that we discussed so far this lesson? Cool. So what I'm going to leave you guys to do is on Canvas, you can get the direct link . No, it's not rotational symmetry. Odd functions have rotational symmetry. But remember, rotational symmetry, Ria, is when you can pick a shape up, pivot it around. So in terms of a cubic, it would be pivoted around the wiggle, the origin, and it needs to land back on top of itself before you get a full 360-degree rotation. That orange curve isn't landing back on top of the original curve. So that means it's not rotational symmetry. Cool. All right. Like I was saying, in Canvas, there's a link to this PDF document already. It won't have any of my notes that we've handwritten in so far today. If you give me a second, I will go back my iPad up and that will, those notes will be there. But at the very end, there are three graphs, three different, they're not three different, two polynomials and one different function that I would like you to sketch the reflection over the x-axis for. So I want you to sketch negative f of x for each of those following functions. So you can see in question A, I've given you 3 points. We know what happens with negative f of x. Those points get reflected. Plot those points and draw what on the same axis, what those would look like. Any questions with that? No? And I might stop our screen recording now because that's the end of what we're doing.